Okay, we are going to move on to chapter 4 here. So that's going to be affine transformations. And in looking at affine transformations, we are going to be interested in, so consider maps F, which take affine n space to affine n space, which preserves some aspect of the geometry of affine n space. Now, the key feature of affine space, certainly from what we've been looking at and in general, is the idea of lines, line segments. So the maps that we're going to consider are going to be those that preserve that aspect of the geometry. There are lots of maps we could consider that don't preserve relevant features of the geometry. For example, you could just take 2 points in affine n space and just swap them over, leaving everything else the same. That wouldn't even be a continuous map. But there are lots of continuous maps we could also consider that don't preserve aspect like, that don't preserve the line structure within affine n space. So we want to preserve the line structure in AN. So by way of a bit of motivation, and because it's part of the definition of an affine transformation, let's just consider what happens when we take a linear map. So I'm going to suppose V is a vector in affine n space or in Euclidean space, and that it's going to be some multiple of another vector by alpha. Then for a linear map, F, we have f of V is alpha f of W. So if you consider the line segment from 0 to V and the line segment from 0 to W, right, those are some multiple of each other in terms of the length, and they are, whatever multiple they are, they get sent to the same multiple. So the ratio between the two line segments is preserved, both to start with and in the image. But the same thing is true, in fact, not just if you take line segments from the origin, but from any other point. So indeed, if P is a point in AN, then P, so the line segment from P to P plus V, and that will be again a multiple of the line segment from P to P plus W, because V and W are multiples of each other. So these go under F to line segments FP to FP plus FV. So I'm again using the fact that F is a linear map here, and similarly to FP and FP plus FW. So the line segment from FP to FP plus FW is a multiple of the line segment from FP to FP plus FW. So even if you start at a different place, this aspect of the of the line structure is preserved under a linear map. But there's another type of transformation which does the same thing, and that's a translation. You can imagine in your head, if you take two line segments that are a certain proportion of each other, you just move them somewhere else, the same thing is true. So the same holds after translation by a point. And putting those two things together, we get the definition of an affine transformation. So I will just write down the definition. 4.1 of an affine transformation. So a map F which takes the affine n space to affine n space is called an affine transformation if there is a point O, NAN, so we can always fix a point O, which we're going to regard as the origin, and a translation vector R, and an invertible linear operator F, which takes the sort of implicit Euclidean n space that we get there from one to another, such that for any point P in AN, what does F do to P? F of P is just equal to, so we start at our origin, we work out where P is from the origin, so that's P minus O, so that's a vector from the origin to P. We apply F to that, and then we translate by R. Now, in simplifying much of this chapter, I decided that it is much more convenient to imagine that we've really picked O to start with, and so this O is in fact going to be just taken to be the 0, 0, and this addition therefore was kind of collapses. So more simply, what we will be writing here is, so more simply, we fix O in a coordinate system, so that's just going to be the point 0, 0, 0, 0, and we just say that f of P is equal to big F of P for this linear operator, and then plus the translation. So this is really a very simple idea. We're just taking invertible linear transformations and allowing ourselves to add vectors to those as well, preserving the line structure. I'll just remark, this is something I've removed from the notes because I don't think it's essential, but you can have a look at it, you can have a go at proving this if you like. So we can characterize affine transformations as those maps F taking AN to AN which send multiples of line segments to multiples of line segments to the same multiples of line segments. So I will leave that as an exercise if you fancy doing it. Right, let's look at some examples. So we'll start with an example 4.2, and there's a nice picture in the notes of this particular example, but I'll treat this in a little bit more of a calculation way to sort of very similar idea. So we'll take the affine transformation F is made up of a rotation about the origin O by 3 pi over 4 radians. So that's 2 pi is a whole thing. Divide that by 8, you get 1/4 pi, so that's 45 degrees. So this is 135 degrees. And a translation by a vector r, which is -3y. So in other words, just assuming that we're fixing a coordinate system where x is going right and y is going up, then this is just going to be pushing us 3 units downwards. So we can see what happens to a point 1, 1, for example. This is x-axis and y-axis. Then the first thing we want to do in applying this affine transformation is to do this rotation, and since it's a rotation by 3 pi over 4, we are going to end up over here. So that is 45 degrees, and so we're going to be round all the way to 180. And we are preserving lengths, of course, because it's a rotation, so it's an orthogonal operator. So this length here, therefore, is going to be the length of this, which is √2. So we're going to move this to the point -2, -√2, 0. And then we're going to move it by r downwards. So this takes us to -√2, 3. So the sort of path that we're going around is a rotation like that, and then a translation like that. Very typically, we'll be representing the matrix of the linear operator here, so the rotation part of this in this example, with a matrix. So in this case, F being a rotation of 3 pi over 4, we know what that is. It's going to be cos of theta, which in this instance will be cos of 3 pi over 4, which is minus 1 over root 2, and then minus sine of 3 pi by 4, which is again minus 1 over root 2, and then sine of 3 pi over 4, which is 1 over root 2, and then cos of this. So that's the vector, that's the matrix representing F, and then of course we can represent R as a vector by 0, minus 3. Okay. Now often what you want to do is to imagine changing the origin. So you express the same affine transformation with respect to a different coordinate system. So example 4.3 is just an example of how that happens. So I'll just go through that. So example 4.3, what does F look like according to a new origin, which will be O dashed, which will be equal to one example we're using is 2, 2. So it will look like some invertible linear operator. So P will map to some invertible linear operator applied to P plus some new translation S. And we want this to represent the same linear, the same affine transformation. So this will also have to be equal to F of P. But here this rotation is now taking place about a different origin, about the origin O dashed. Now, if you're rotating about an origin, then that point is going to be fixed. So we can actually use this equation here to work out what S is if we just plug in 0 dashed. So plugging in 0 dashed, the origin, new origin, we know that this linear operator is going to fix it because that's the one that is rotating about that point. So we'll get 0 dashed plus S is equal to, and because we're regarding this in this coordinate system as just being 0, so this is kind of just equal to S, that's going to be the point in the old coordinate system that we got by just applying F to the origin. And we had a matrix for that that's just over here. Just turn that to here. So we're going to just apply F to the point 2, 2, and then do our translation by R. And it'll give us our new translation. F of 2, 2 plus R. And if you work that out, then this turns out to be minus 2 root 2, 0. And R here, of course, is 0 minus 3. And so, adding all that together, we get that our new translation vector is just going to be minus 2 root 2 minus 3. So that is explains the example 4.3. Okay, so the last thing we will do in this video is go through proposition 4.4, which is really just an opportunity for us to test out some of these ideas, but it fundamentally it's telling you something like 3 points determine a plane. So this is proposition 4.4. So any affine transformation F sending A2 to A2, so two-dimensional affine space, two-dimensional affine space, is determined by the image of any three non-collinear points. And the way that we'll prove this is just going to be by thinking of one of the non-collinear points as being the origin. May as well just pick one of them to be the origin, and then the other two are going to allow us to work out what the invertible linear transformation is, and where the origin goes will tell us where the what the translation vector is. So I've just told you the proof, but we'll just write it out. So let O, P1 and P2 be the three non-collinear, sorry, I missed an L there, it should be two L's, non-collinear points so since P1 minus O and P2 minus O are so they can't possibly be parallel because these are not these three things in a line, and so when I take these 2 points, when I take the origin away, take the vector that goes from one to the other, those are also not going to be parallel. So these are linearly independent. And so they form the basis of Euclidean Euclidean 2 space. Hence, the images under the invertible linear map so the invertible linear map F takes us from one basis to another, and so determines so are linearly independent as well, and so determines F completely. And then finally, to work out what the translation is, you just apply it to the origin. Finally, F of O equals R determines the translation vector. Okay. We'll see how affine transformations can be used to help us classify the conic sections. So we'll see how two ellipses in particular are taken, any one of them to any other one, by an affine linear transformation, and that will try to connect some of the different notions of conic sections that we've come across so far.